So in addition to the review sheet that I uploaded to Canvas along with the solutions, I thought it would be good to do a super fast speed through a whole bunch of the key concepts, see if I can get this done in a reasonable amount of time, to just give you a little something to refresh your mind on each of these major topics here. So this is a list of things that you should know going into your second exam for calculus. Now, there's some things here that I expect you to know how to do, such as basic derivatives. That is something that I'm not going to review at this point. If you don't know how to take the derivative of x squared, you probably don't even want to be taking this exam. But I know all of you know how to do that, so we're going to hit up some of these other highlights here. So we're just going to run through each of these. So the first thing is the limit definition. So remember, we defined this to be the limit as h tends to 0 of f of x plus h minus f of x divided by h. This came from looking at secant lines and the slope. So this is going to be the change in y over the change in x, and we took the limit as h goes to 0. So you want to evaluate this expression, simplify things down. Once you're able to cancel the h's, then you take the limit, and that is your limit definition. Next thing we want to talk about are tangent lines. So remember here, the derivative at a point is equal to the slope of the tangent line. This was the main motivation of what we started looking at. We looked at secant lines and said that these secant lines would, as we get closer and closer to something, it's going to do a better approximation of the slope of the tangent line. So indeed, the derivative at a point, that number gives you the slope of the tangent line at that point. All right, chain rule, quotient rule, product rule. So remember, the product rule here, so if we do an example of, say, f of x is equal to x squared secant x, if we take the derivative, remember, the rule said we take the first times the derivative of the second. The derivative of secant is going to be tangent x secant x. First times the derivative of the second plus the second times the derivative of the first. So that is your product rule. If we do something like the quotient rule, and I do say f of x is equal to, say, sine of x divided by 3x plus 2, so the derivative is going to be the bottom, which is 3x plus 2, times the derivative of the top, which is cosine x, minus the top, which is sine x, times the derivative of the bottom, which is 3, and that is all over the bottom squared. And then we have the chain rule, and so what the chain rule said that is if you have functions inside other functions, you have to multiply by derivatives of the inner things as well. So if we have, say, f of x is equal to, say, cosine to the fourth of, say, 2x, if I take the derivative of this, I have to look at the outermost function. This could be rewritten as cosine of 2x, all of this raised to the fourth. My outermost function is to the fourth power, or u to the fourth. I do 4, move down the exponent. I rewrite the inside. I raise that to the third power. So I do my basic something to the fourth power, bring down the exponent, subtract 1 from the exponent, rewrite the inside. Now the next outermost function I have is cosine, so I take the derivative of cosine, which we know is negative sine. I rewrite the inside, and then now I have to take the derivative of the inside, and that's 2. So chain rule can be repeated multiple times. Also, as a reminder, you can combine all of these. You can have a function that has a chain rule with a product rule and a quotient rule all together in one. So make sure that whenever you take a derivative, you're thinking, what rule do I need to use? Because for an example, if we had one that looked like f of x is equal to x cosine x over 4x plus 3, you would have to combine both the quotient rule that you would do first, but to take the derivative of the numerator, you have to do the product rule. So make sure that you can combine all of these in one. All right, now position velocity acceleration, the derivative of position is velocity. The derivative of velocity is acceleration. That means the second derivative of position is acceleration. Related rates. So remember, with related rates, the key idea, so related rates, what you need to do is you need to find a formula to relate variables. Then you're going to do implicit differentiation, and then you're going to plug in info from the snapshot. So remember, all of these are times in which you want to be able to relate various things together, and then you're going to try to take the implicit differentiation with respect to time, and then at a specific moment, things are going to be changing. You're going to plug in that specific moment to find whatever it is that your question is looking for. So speaking of implicit differentiation, remember, with an implicit differentiation, we're basically using the chain rule. So if we had something like, say, xy is equal to cosine of x squared plus xy. So if this is my derivative and I want to do this implicitly, we cannot explicitly solve for y. We can't write y equals something with just only x's. So because y is in the middle of this, we now have to take the derivative implicitly. So what that means is the first step is you take the derivative of both sides with respect to x. Then once you set this up, now you just take the derivative of both of these sides, making sure that you have the correct process. So here we need to use the product rule. So we have the first times the derivative of the second plus the second times the derivative of the first. So remember, the derivative of y is going to be y squared. The derivative of y always has to be dy dx. We don't know what the derivative of y is, so we say dy dx. Then over here, I have to use the chain rule. So I take the derivative of the inside, which is, or the derivative of the outside, which is negative sine. I rewrite the inside. And then now I have to multiply by the derivative of the inside. So this requires us now to use, this first rule is just basic. We have 2x. Here we have to use the product rule again. So I have the first, the derivative of y squared is 2y, but remember we have dy dx. So it's basically the chain rule plus the second function times the derivative of the first. And that is the derivative part of this. And then the last thing you want to do is you want to solve for dy dx. So you want to get the dy dx's to one side. Now, if you're looking for the slope of a line at a point, I would plug in x and y at this point. So on your homework that you had a while ago, you might have been given the point, say x equals 0 and y equals, 2. Plug that in right now, find dy dx with just numbers. It'll make your life a lot easier. Absolute extrema. So remember, we had things like relative and absolute extrema. So when we're looking at absolute extrema, the process that we did often was on a closed interval. So if we want the absolute extrema on a closed interval, what we need to do is we need to find the critical values in the interval. So critical values, we can skip ahead and say, what if we look at critical values? What are these? These are going to be places where the derivative equals 0 or the derivative is undefined. So you find those points, figure out what those are, and then what you do is you now make a list with these critical values and endpoints. And then you evaluate the function at each. So if we're going to try to find the absolute maximum, we evaluate the function of all of those, pick the largest one, that's your absolute max, the smallest one will be your absolute minimum. For a continuous function on a closed interval, there will always, always, always be an absolute extrema, an absolute max, and absolute min. Optimization, so this is going to be somewhat similar to related rates. However, the big difference now is that optimizing it, we're trying to find what is going to be the maximum or what is going to be a minimum. So with related rates, we just wanted to see how is things changing with respect to time. Here, we're trying to figure out what is the absolute biggest or absolute smallest. So for your optimization, again, what you need to do is you need to create a formula. So some formula that relates the situation that you're looking in, be it areas, volumes, could be looking at profits, whatever, then you're going to find the max/min, and often you have to use the constraint. So usually there's something that says you can't just have all possible values. We have something that's restricted, so we're going to use the constraint, help us be able to get our function into a single variable. Then taking the derivative is very easy, and then if you have a closed interval, you do exactly what we did with absolute extrema. If you do not have a closed interval, we had to use that other theorem that says that if you have a local maximum or relative maximum, and it's the only critical value, that is an absolute maximum, or the same thing with a minimum. So that's optimization. Graph sketching. So remember, when we want to sketch a graph, we can use information about first and second derivatives. We can use information about where derivatives don't exist, that type of things. But remember, we have these different types of shapes that might occur. So this would be something, our function will take on this shape when it is decreasing and it is concave up. It might take on this case where it is increasing but it's concave down. It might do something like this, where this is decreasing and it's concave down, or it might look like this, where this is increasing and it's concave up. So when you sketch a graph, you're going to have these four possible shapes, depending on what your first and your second derivative, if those are positive and negative, and then you just piece all of that together when you are doing your graph sketching. And so you have to figure out where the derivative and where the second derivative are positive and negative by drawing a number line, testing points in between each of those. Newton's method, we had a way to find roots. So this was a way to approximate roots for a polynomial or just any old function. You could be able to you take an initial approximation and you say, okay, that's decent. Then you use the formula for Newton's method. So that was going to be x of n plus 1 is equal to x of n minus f of x of n divided by x prime at x of n. So we programmed this into our calculators. You put in your derivative and your function into y1 and y2. You programmed it, and then it would repeatedly give you better and better approximations. And all of this was going to be done numerically, and so we don't expect a perfect number. We just want to be able to compare previous numbers and say, these same decimals keep appearing. I know my solution is going to be accurate to that amount. Tangent line approximation was something that said that if we have a function, the tangent line is going to be pretty close to that, near that point. So we were able to approximate things using the tangent line because it's a lot easier to evaluate something like a tangent line. So we could do an example of, say, f of x is equal to, say, sine of 0.02. If I want to approximate this number, that's really hard to do. But you could find what is the tangent line at this point. So you'll find the tangent line to sine of x near x is equal to 0. So you find the tangent line of the function sine near a number that's close to where you're trying to approximate it, and then you plug in 0.02 into that line, and that's going to be the way you solve it. If we instead wanted to do something like, say, approximate sine of 3, where this is, again, this is in radians that we're thinking, we're going to be doing this near x is equal to pi, because finding sine of pi is a lot easier. We're going to use the power of linear approximations for things like that. Relative extrema. So remember, we have things, there's a difference between relative or local extrema versus absolute. So if we have a function that is increasing and then decreasing, as long as this point is defined here, this is going to be a relative max. If it is decreasing and increasing, we have a relative min. And all of this has to do with your first derivative, because where your derivative is positive, it's increasing. Where your derivative is negative, it is decreasing. So you're able to look at a first derivative to find those. You could also use a second derivative test. So the second derivative test of that, if you have some type of maximum here, you have concave down. So if this point is a critical value, you evaluate the second derivative at it and it is negative, this is going to be a concave down function, which implies this is going to be a maximum. Again, a relative maximum. Or same thing if you have a critical value here, so the derivative equals 0, say